All right. So I need to start doing this a little bit earlier. So that's something I'm going to try to push this week. That's going to be my goal this week. Try to get one early morning session in, and then maybe do just some stuff during the afternoon. I just got to figure out how to do it. But it's time to start dissecting a textbook. I want to kind of play around with that. Downloaded the book onto my Chromebook. And so, oops. Here we go. And I'm able to use my little draw pad on here. So, oops. There we go. There we go. Smiley face. So let's go ahead and zoom out a little bit. 175. Yep. 150. 125. Yeah, that looks good. And then I think each page I go through, I should mark it when I'm done with initial. So green, smiley face, smiley face. Not going to do that one. Don't really care about that one. Oh, whoops. I forgot it does that sometimes. These images that are like intense. Oh, weird. Oh, let's see. There we go. Okay, so start. And the goal is to get through this. So, chapter 1, prerequisites. So there's an introduction to prerequisites on page 7, so beginning. And then section 1.1, real numbers, algebra essentials. 1.2, exponents and scientific notation. 1.3, radicals and rational exponents. 1.4, polynomials. 1.5, factoring polynomials. 1.6, rational expressions. So I'm going to go ahead and let's go blue for the next part. We're going to connect the beginning and end through this. And I was going to say something. Just go ahead and put so it'll be 10, 5, 20, 23. Just trying to play around with some stuff right now. I want to figure. I don't know how I'm going to do this as a method. So I've got to play around with different ideas to see what works and what doesn't. So it might be different. I might figure it out my first try. Who knows? But and then when I end it, I will mark the date and the time. Let's do 1700. So 5 o'clock p.m. our time. Yeah, and then I guess just figure this stuff out as I go. I'm going to pause for a second. Need to think about something. All right, got my thoughts together. I know what I was going to do. So I'm going to do 3. Read, and then that's going to split off into 2. And then I'm going to have write, and so let's speak, write, type. Yeah, so that's what I'll do. So read, write, and type, and then they'll come back together. And then summarize. Actually, let's rewrite that. Let's pop that. Okay. Oh, that was interesting. There wasn't enough room there. So, but yeah, summarize. And so basically, the idea is by reading it in whatever format it's in, that will expose me to the words. And then by writing and typing it, I'm essentially breaking it down into the tactile sensations that were originally used to come up with the ideas. So I've expressed it in 2 local ways. Fingertips being a more multiplicative, so I have multiple fingers doing one thing, and then I have one whole object doing one thing by writing. And then summarizing. So then, yeah, I'll break it down and then I'll put it all together in the way that makes the most sense to me. And that is the first step. So it's like a 3-part process. So let's move this up a little bit. 3-phase, reading, or multiphasic. And then by reading it out loud through the spoken word, it's like exposing my whole body to essentially the imprint that is the book. And then by going more dualistic in the tactile sensation way of doing it, I'm getting basically 3 different perspectives. I'm getting finger taps versus whole hand taps versus vocal cords vibrating. So it's 3 different ways. That's actually kind of akin to what I've read in the Bible about needing 3 parties to witness something. And then once I've completed that, then I can summarize. And then the goal is to summarize it. What does summarize mean? Summarize. So that's going to start out with a brief wordplay. And then that's going to go to imagery. And that's going to go to movery. Basically moving images, video. That just seems to be the logical conclusion. And then that'll allow me to explain things in three different ways. I like that. Okay, so first, I've already read Algebra Chapter 1. So now, and actually, let me validate that. I can prove that. I think that's what I think that makes. I think that makes smarter people. Instead of complaining about things and being like, "Oh, I wish you would have done this." It's like, "Oh, I can demonstrate it." So let's go down to next page. I went through a phase. That's when I'll find it. Openstax, philosophy, Openstax, Algebra Trig 1, right there. However, I will be changing the way I read now. I'm going to include note taking. So this was just sort of a practice step. So let's go ahead. So we'll go ahead and start Chapter 1, Prerequisites. So that, I believe, was page 17, according to the PDF reader that I'm reading from. That's it. Prerequisite. Okay. I'm going to write the time in red for each of these, before and after. So 5:14. Okay. Real numbers, algebra essentials is the first section. So, introduction to prerequisites. It's a cold day in Antarctica. In fact, it's always a cold day in Antarctica. Earth's southernmost continent, Antarctica experiences the coldest, driest, and windiest conditions known. The coldest temperature ever recorded, over 100 degrees below zero on the Celsius scale, was recorded by remote satellite. It was no surprise then that no native human population can survive the harsh conditions. Only explorers and scientists brave the environment for any length of time. Measuring and recording the characteristics of weather conditions in Antarctica requires a use of different kinds of numbers. For tens of thousands of years, humans have undertaken methods to tally, track, and record numerical information. While we don't know much about their usage, the Lubombo bone, dated to about 35,000 BCE, and the Ashango bone, dated to about 20,000 BCE, are among the earliest mathematical artifacts. Found in Africa, their clearly deliberate groupings of notches may have been used to track time, moon cycles, or other information. Performing calculations with them and using the results to make predictions requires an understanding of relationships among numbers. In this chapter, we will review sets of numbers and properties of operations used to manipulate numbers. This understanding will serve as prerequisite knowledge throughout our study of algebra and trigonometry. All right, 1.1, Real Numbers, Algebra Essentials. Learning objectives. In this section, you will classify a real number as a natural, whole, integer, rational, or irrational number. Perform calculations using orders of operations. Use the following properties of real numbers: commutative, associative, distributive, inverse, and identity. Evaluate algebraic expressions. Simplify algebraic expressions. All right, here we go. It is often said that mathematics is the language of science. If this is true, then an essential part of the language of mathematics is numbers. And actually, I'm going to disagree with that. Science and mathematics are languages that bolster each other. They don't necessarily represent each other. Because there's a lot of math that I've seen that, like, you would ask, like, why would we use that at all? And in most cases, you just wouldn't. So I think it's a little more complex than that's saying. Okay, sorry. If this is true, then an essential part of the language of mathematics is numbers. The earliest use of numbers occurred 100 centuries ago in the Middle East to count or enumerate items. Farmers, cattle herders, and traders used tokens, stones, or markers to signify a single quantity, a sheaf of grain, a head of livestock, or a fixed length of cloth, for example. Doing so made commerce possible, leading to improved communications and the spread of civilization. 3 to 4,000 years ago, Egyptians introduced fractions. They first used them to show reciprocals. Later, they used them to represent the amount when a quantity was divided into equal parts. But what if there were no cattle to trade or an entire crop of grain was lost in a flood? How would someone indicate the existence of nothing? From earliest times, people had thought of a base state while counting and used various symbols to represent this null condition. However, it was not until about the 5th century CE in India that zero was added to the number system and used as a numeral in calculations. Clearly, there was also need for numbers to represent loss or debt in India in the 7th century CE. Negative numbers were used as solutions to mathematical equations and commercial debts. The opposites of the counting numbers expanded the number system even further. Because of the evolution of the number system, we can now perform complex calculations using these and other categories of real numbers. In this section, we will explore sets of numbers, calculations with different kinds of numbers, and the use of numbers in expressions. Classifying a real number. The numbers we use for counting or enumerating items are the natural numbers. Okay, I'm going to go ahead and just pop the highlighter thing up. Custom. Let's do green. Of the natural numbers. Oh, cool. Okay. And that's going to include the numbers 1, 2, 3, 4, and 5, and so on. Now, actually, before we get through this, I'm going to go ahead and just show. Let's go ahead and pop pen out. Palette. Yep. So I'm using the base 10 number system where each digit can be represented by the following 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and can go on for I'm going to draw that. N equals 0, N equals infinity. So as it goes on, each of these spaces can hold one digit each space. Dot, 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 dot. Let's do that. Okay. Like that. That's the way I think about it. So each of these can hold one of these 10 digits. That's the whole basis of algebra. Algebra is like in this one spot, it can be any one of these 10. In this one spot, it can be any of these 10. In this one spot, it can be any of these 10, and so on and so on. So just wanted to describe that's the way I was thinking using those numbers. So we describe them in set notation as, and then they use the brackets. And then inside the brackets, it's 1, 2, 3, dot, dot, dot. So let's go ahead and just underline that. Where the ellipses, dot, 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 indicates that the numbers continue to infinity. The natural numbers are, of course, also called the counting numbers. Anytime we enumerate the members of a team, count the coins in a collection, or tally the trees in a grove, we are using the set of natural numbers. The set of whole numbers, let's go ahead and pop that. Quantum numbers. Anytime we enumerate the members of a team, count the coins in collection. Oh yeah, then the set of whole numbers is a set of natural numbers plus 0. And so there's the set right there. Okay. The set of integers. Oops. This highlighter isn't very good. Okay, never mind. I'm not gonna do highlighters. I'm just gonna underline. Adds the opposites of the natural numbers to the set of whole numbers. So it includes, in addition to the whole numbers, you have all the negative variants, or essentially the variant with the opposite polarity. That's where shapes come in. It is useful to note that the set of integers is made up of 3 distinct subsets: negative integers, 0, and positive integers. So let's actually negative. Let's do gray, 0, and then green for positive. Positive. In this sense, the positive integers are just the natural numbers. Another way to think about it is that the natural numbers are a subset of the integers. The set of rational numbers is written as, and then in the set bracket notation, m divided by n, such that m and n are integers and n does not equal 0. So any fraction such that the denominator of the fraction is not 0. Because when you put the 0 in the denominator, that's where things get wonky. And that's why I don't treat 0 as a real number, like an actual number. It's a distance from a chosen center. And I can explain that more later. Notice from the definition that rational numbers are fractions or quotients containing integers in both the numerator and the denominator, and the denominator is never 0. We can also see that every natural number, whole number, and integer is a rational number with a denominator of 1. So what it's saying there, I'll just do right here. It's saying that a whole number, let's choose 5. That's a whole number. That's the same as saying 5 over 1, which is rational. They're the same exact thing, but they belong to different sets. Anyway, because they are fractions, any rational number can also be expressed in decimal form. Any rational number can be represented as either a terminating decimal, such that the example they use is 15 over 8, which is 1.875, and so it terminates because after that 5, there's no further. We don't need anything else. Everything else is just kind of a placeholder. It's arbitrarily there. And then a repeating decimal. So the example they use is 4 divided by 11, which is 0.36363636. And so they use 0.36 with a bar over it. That just means that 36 repeats itself over and over again. We use a line drawn over the repeating block of numbers instead of writing the group multiple times. All right, let's go ahead and hit up this example. I'm just going to read this from front to back. So example 1, let's just go down to here. All right, writing integers as rational numbers. Write each of the following as a rational number. Well, if it's supposed to be rational, we just said that to turn a whole number into rational, you just put it out divided by 1, because that's the same thing as just saying the numerator by itself. So be 7 over 1, 0 over 1, and negative 8 over 1. Yep. Okay. Example 2. Right. Identifying rational numbers. Write each of the following rational numbers as either a terminating or repeating decimal. Okay, well, let's just demonstrate, I guess, with a little bit of long division, because I actually want to demonstrate that that's something that everyone should be able to do. So I'm just going to do it right up here. Negative 5 divided by 7. See if I remember how to do this. It's been a while. So that's the same as saying 7 on the outside, 5 on the inside. Goes in there 7 times for 9. So that's going to go over once. Nope, that goes there. Sorry. This is how I just mentally visualize this. Let's get rid of that decimal. Okay. So that gives me 1, 0, 1. Yep, so 0.71. And if I were to continue doing that, I would eventually get to that answer. So let's see if I can get to there. 10, 7, 3, 0. Goes in there 3 times. 27, 3. Did I screw that up somewhere? Sorry, 28. Shoot. 4 times. I actually did 9 in my head. So that's 28, 2, 0, twice. That gives 14. So 20 minus 14 is 6. 0, 8, 56. Yep. 5, 35. Yep. 5, sorry. And then there it is. And then I should expect it to repeat itself. So cool. That's good practice of doing that. So I do remember how to do that. 15 over 5. That's just 3. So it's a terminating decimal. Yep. And then 13 divided by 25. Out of 25, since it's a multiple of 5, that's going to terminate. I just know that. So at least that's the way I think it should. That was my expectation, at least. Okay. All right. Irrational numbers. At some point in the ancient past, someone discovered that not all numbers are rational numbers. A builder, for instance, may have found that the diagonal of a square with unit sides was not 2 or even 3 halves, but was something else. Or a garment maker might have observed that the ratio of the circumference to the diameter of a roll of cloth was a little bit more than 3, but still not a rational number. Such numbers are said to be irrational because they cannot be written as fractions. These numbers make up the set of irrational numbers. Irrational numbers cannot be expressed as a fraction of 2 integers. It is impossible to describe this set of numbers by a single rule except to say that a number is irrational if it is not rational. So they set builder notation. Oh, I meant to underline this. Sorry. There we go. And then a little set builder notation there. H, where H is defined as not a rational number. Okay. All right. Example 3, differentiating rational and irrational numbers. Determine whether each of the following numbers is rational or irrational. If it is rational, determine whether it is a terminating or repeating decimal. Root 25, I know that just off of memory, that's 5. That's terminating. 33 ninths can be reduced. Divide by 3, it's 11 thirds. That's going to be repeating because over 3 You're going to have 0.3s repeating or 0.6s repeating. Root 11, I would assume that's irrational. So that would be repeating. 17 over 34, that's 1/2. That's terminating. And then that's repeating, it looks like. Let's see. Oh, sorry. Rational. I guess I forgot to talk about rationality. Yeah, because it's predictable. It makes it rational. If it's irrational, it's something that cannot be simplified any further. So by using that convention with the little line over it, that's what makes it rational. So then that last one is not rational. Yep. Okay. All right. Oh, I didn't even see these try-its. I'll do those before doing the problems. All right, so real numbers. Given any number n, we know that n is either rational or irrational. It cannot be both. The sets of rational and irrational numbers together make up the set of real numbers. As we saw with integers, the real numbers can be divided into 3 subsets: negative real numbers, 0, and positive real numbers. Each subset includes fractions, decimals, and irrational numbers according to their algebraic sign, positive or negative. 0 is considered neither positive nor negative. The real numbers can be visualized on a horizontal number line with an arbitrary point chosen as 0, with negative numbers to the left of 0 and positive numbers to the right of 0. A fixed unit distance is then used to mark off each integer or other basic value on either side of 0. Meant to underline. Any real number corresponds to a unique position on the number line. The converse is also true. Each location on the number line corresponds to exactly one real number. This is known as a one-to-one correspondence. We refer to this as the real number line, as shown in figure 1. The real number line. Let's go ahead and circle that little guy. So there's the real number line. Number lines are very useful. Okay. Example 4, classifying real numbers. Classify each number as either positive or negative, and either rational or irrational. Does the number lie to the left or to the right of 0 on the number line? So by convention, negative, let's keep it there. Negative equals left of 0. Positive equals right of 0. And so just by looking at the sign, I can define, so A, C, and D are all negatives, so they are to the left of 0. And we have rational, irrational, rational, rational, and irrational. And then B is irrational, C is irrational, both positive. Negative rational, positive irrational, negative rational, negative irrational. Sorry, repeating decimal. I wasn't paying attention to the ellipses. So if you have the ellipses, that defines rational because it's predictable. but it's also positive. Right? Sets of numbers as subsets. Beginning with the natural numbers, we have expanded each set to form a larger set, meaning that there is a subset relationship between the sets of numbers we have encountered so far. These relationships become more obvious when seen as a diagram, such as figure 2. There's figure 2. So in figure 2, we have the natty boys. That's me. I'm Nathan. We've got the holes. So by just putting that one little dude there, you make that whole thing whole. And then that's the integers. So you have polarity involved. So that's count plus direction, because you're adding a direction to that, basically a whole dimension to that. And then Q is the rational numbers. And then anything that's not a part of any of that is irrational. Or outside of the box. Number exists because it exists. Cool. All right. There's a little definition, little doohickey down there. Sets of numbers. The set of natural numbers includes the numbers used for counting. The set of whole numbers is the set of natural numbers plus 0. The set of integers adds the negative natural numbers to the set of whole numbers. The set of rational numbers includes fractions written as... I actually don't like the way they described this. I'm going to delete it. No. Sad face. It's the negative natural numbers plus 0 plus the natural numbers. Because 0 and the positive numbers have nothing to really do with each other besides the fact that just 0 is a bridge. Okay. The rational numbers includes fractions written as m divided by n, such that m and n are integers, and n does not equal 0. The set of irrational numbers is the set of numbers that are not rational, are not non-repeating, and non-terminating. Example 5. Differentiating the sets of numbers. Classify each number as being a natural number, whole number, integer, rational number, and or irrational number. So A is a natural number because it's a positive whole number. 8 over 3 is going to be a rational number. Root 73, I'm guessing 73 sounds prime just in my head. So I'm guessing it's irrational. Negative 6 is going to be an integer. And then that is repeatable, so it is a rational number. Oh, I didn't think about it just including it in all the sets. But yeah, so the first one actually is part of 4 of the 5 sets. It's all but irrational. And then 2.6, that's just rational. Root 73 is just irrational. Negative 6 is going to be an integer and rational. And E is just irrational. But it's got the repeating pattern, though. Yeah, so that's a typo. Typo. These books do have them. So should be should be rational because ellipses. Without the ellipses, it becomes irrational. Okay, cool. Next, performing calculations using the order of operations. When we multiply a number by itself, we use it or raise it to a power of 2. For example, 4 to the power of 2 equals 4 times 4 equals 16. We can raise any number to any power. In general, the exponential notation a raised to the n power means that the number or variable a is used as a factor n times. So a to the n is a times a times a, and so on n times. In this notation, a to the n is read as the nth power of a, or a to the n, where a is called the base, and n is called the exponent. So base is the foundation, and the exponent is how far it gets raised. A term in exponential notation may be part of a mathematical expression, which is a combination of numbers and operations. For example, 24 plus 6 times 2 over 3 minus 4 squared is a mathematical expression. To evaluate a mathematical expression, we perform the various operations. However, we do not perform them in any random order. We use the order of operations, and I have to make a statement before we continue. Order of operations, let's go down here. Order of operations is by definition chosen given the desired conclusion. So the definition that is chosen by this book is PEMDAS. Parentheses, first, exponents, second, multiplication and division is third, addition is fourth. Why? Because all of these higher orders are built on a lower order, are built on a lower order operation. Multiplication is addition with limitations. Just sort of depending on what you're doing. But basically multiplication, and I'll describe that here. Let's do 25 times 5. Well, that's the same as 5 times 5 times 5. But 5 times 5 equals, oops, I didn't mean to hold that down. 5 times 5 equals 5 plus 5 plus 5 plus 5 plus 5. And I can replace that for every multiplication that I see. It's just a higher order because you're adding a bunch of things. So I'm doing 5 operations. That's 5 operations in 2 operations, right? And it's higher order because I can do the same thing with less. So, anywho, Sorry. But it's completely arbitrary, but for the case of this book, always assume parentheses first, then exponents, then multiplication and division, then addition and subtraction. So the way I see it is a parentheses is like it's creating a target. I'm focused on inside of that first. So, and then exponents, it's higher order because the way it's written, it's higher up than the actual base number. So do those next, so on. Cool. All right. Anywho, recall that in mathematics we use parentheses, brackets, and braces. So those are the three different types of enclosures. I'm going to call them that. I like that word. I like that. enclosures, enclosures. To group numbers and expressions so that anything appearing within the symbols is treated as a unit. Additionally, fraction bars, radicals, and absolute value bars are treated as grouping symbols. When evaluating a mathematical expression, begin by simplifying expressions within grouping symbols. The next step is to address any exponents or radicals. Afterward, perform multiplication and division from left to right, and finally, addition and subtraction from left to right. And remember, even the whole left to right argument is arbitrary. Because, especially usually in the way that we do the math, doing it one way is the same as doing it the other way. So let's take a look at the expression provided. 24 plus 6 times 2 over 3 minus 4 squared. There are no grouping symbols, so we move on to exponents or radicals. So there's no grouping symbols, or, as I called them, enclosures. So we move on to expressions or radicals. The number 4 is raised to a power of 2, so simplify 4 squared as 16. So if I added to this, just to clarify, it's redundant because of the rules that we're following, but if we were to do this in a general sense, where 4 squared equals 16, you can add on 4 times 4 equals 4 plus 4 plus 4 plus 4. So it doesn't matter. It's all the same thing. And then you get that. And then you just substitute that in. Next, perform multiplication or division from left to right. 24 plus 6 times 2 over 3 minus 16. So you get 24 plus 4 and then minus 16. So what happened is we're going to do that. That's next. That's the next step. So 6 times 2 over 3 equals 6 over 1 times 2 over 3 equals 12 over 3 equals 4. Oh, look, there's the 4. Perfect. Okay. Lastly, perform addition or subtraction left to right. 24 plus 4 minus 16. So then you get 24 minus 16. So we'll do, it looks like they just did this one next, where 24 plus 4 equals 28. That's that. And then they're going to do that next. 28 minus 16. And then that replaces that. Therefore, 24 plus 6 times 2/3 minus 4 squared equals 12. For some complicated expressions, several passes through the order of operations will be needed. For instance, there may be a radical expression inside parentheses that must be simplified before the parentheses are evaluated. Following the order of operations ensures that anyone simplifying the same mathematical expression will get the same result. So order of operations is defined by the PEMDAS, is how they're doing it. Parentheses first, then exponents, multiplication, division, addition, subtraction. Where multiplication and division are the same order, addition, subtraction are the same order, so you just do it from left to right. Okay? How to. Given a mathematical expression, simplify it using the order of operations. Step 1, simplify any expression within the enclosures. Step 2, simplify any expressions containing exponents or radicals. Step 3, perform any multiplication or division in order from left to right. Step 4, perform any addition and subtraction in order from left to right. Okay, example 6. Use the order of operations to evaluate each of the following expressions. Okay, let's see if I can go ahead and select tool. Oops. Oh, I guess I can't select that. Okay, never mind. It's not going to work that way. Okay, let's just go ahead and do that. And then let's go ahead and open up a Google Keep. And we'll go ahead and pop into here. Okay. Okay, bookmarks. Examples. Let's do my examples in here. Okay, so let's go ahead and shorten that up. And then let's bring that over there. Okay. Okay, so let's go ahead and just write these down. 3 times 2 squared minus 4, 6 plus 2. And then 5 squared minus 4 over 7 minus root 11 minus 2. 6 minus 8 plus 4 minus 1. It's hard to see that one. I'm just going to say that's 14 minus 3 times 2 over 2 times 5 minus 3 squared. And then 7, 5 times 3 minus 2, 6 minus 3 minus 4 squared plus 1. Okay. All right. Okay. All right. So using PEMDAS, those order of operations. So here, 1 will be parentheses. And so you get 3 times 2, so that's going to be 6 squared minus 4 times 8. So exponents next. So that's going to be 36 minus 32 equals 4. All right, next one. So I'm going to break this up into, let's see. So this is an exponent. So the radical is an exponent. So it's like saying, I'm going to rewrite, and that's going to be 5 squared minus 4 parentheses times 1 over 7 minus 11 minus 2 to the 1/2 power. So, parentheses first. 5 squared minus 4. That's the same as saying 25 minus 4 equals 21. Times 1 over 7. That's going to equal 21 divided by 7. That's 3. So you got 3 minus, and then 11 minus 2 is 9. 9 to the 1/2. But that's the same as saying square root. So that equals 3 minus 3 equals 0. Next. So this is an enclosure. I'm going to draw the arrow towards that. The absolute value is an enclosure, so I'm going to do enclosures first on this one. 5 minus 8 is -3, so 6 minus -3 plus 4 minus 1 is 3. Absolute value of -3 makes it +3. 6 minus +3 is 3, plus 3 is 6. So 6 minus 3 plus 3 equals 6. That's if I did it right. All right, we can do some shortcuts. 3 squared is 9. So this is like saying 14 minus 3 times 2 times 1 over 2 times 5 minus 9. So that's 6. 14 minus 6 is 8 times 10 minus 9 is 1. That's 1. 8 times 1 is 8. That's if I'm doing it right. I'm doing a lot of this in my head, so that's 15. That's 3. That's 16. So -7 times 15. 105 minus 2 times 3 minus 16. So -13. Absolute value plus 1. So 105 so value 13. 26. It's positive, so -26. 105. 26 plus 1. It's 105 minus 25. 80. All right, so if I did it right, let's see. Cool if I make mistakes, though. Uh-oh. Uh-oh. There we go. There we go. 4, 0. 4, 0. 12. Did I say 6? I said 6. I screwed up somewhere. Eight, 132. I'm off on all of those. Okay, let's try this again. Okay, let's do this again. So 6 minus, oh, this color sucks. Let's go here. 6 minus 5 minus 8 plus 4 minus 1. Okay, well, that's 3. So 6 minus, oops, maybe 3 plus 3. Nope. Okay, what did I do wrong? Oh, I started it wrong, so I don't need to worry about that. I would have gotten it right. Oh, I didn't think I got that one right. Okay, I got that one right. Okay, and the last one I got wrong. So let's do this again. Here, 7, 5 times 3, 2, 6 minus 3 minus 4 squared plus 1. Let's make sure that's right. Okay. 7 times 15 minus 2 bracket, or sorry, absolute value, 6 minus 3. So that's 3 minus 16 plus 1. So that's 105 minus 2. 3 minus 16 is negative 13 plus 1. That's positive 13. Oops. Yep, there's our problem. You forgot the absolute value. So once you do, just do this. Once you do just this part, 3 minus 4 squared, 3 minus 16 equals negative 13. Then you absolute value it. So then you get 13. So minus 2 times 13 plus 1. 26 plus 1. Negative 26 plus 1. 25. So it's 80. My answer's right, in my opinion. I could be wrong. I could be doing the order wrong somehow, but I just don't see how they took out the absolute value sign. So I'm going to assume that that was a typo. Okay. Right. Using properties of real numbers. For some activities we perform, the order of certain operations does not matter, but the order of other operations does. For example, it does not make a difference if we put on the right shoe before the left or vice versa. However, it does matter whether we put on the shoes or socks first. The same thing is true for operations in mathematics. Commutative properties. The commutative property of addition states that numbers may be added in any order without affecting the sum. So a plus b equals b plus a. So it means if you read it from left to right, you should get the same answer as if you read from right to left. So if I do it this way, left to right equals right to left. That's a T. Gosh, I hate it when I do that. All right, similarly, we can better see this relationship when using real numbers. And so they just throw some real numbers in. Negative 2 plus 7. So left to right. That's a T. Left to right equals 5. Right to left equals 5. Commutative. Check mark, smiley face. Cylinder. Okay. All right. Similarly, the commutative property of multiplication states that numbers may be multiplied in any order without affecting the product. So like the commutative of addition, the only difference is the sign now, and then obviously the operation that's done with the sign. But remember, multiplication, and the way we use it here, is the same as addition. So a times b equals b times a. Again, consider an example of real numbers. Negative 11 times negative 4 equals 44, and negative 4 times negative 11 equals 44. It is important to note that neither subtraction nor division is commutative. For example, 17 minus 5 is not the same as 5 minus 17. Similarly, 20 divided by 5 does not equal 5 divided by 20. So, associative properties. The associative property of multiplication tells us that it does not matter how we group numbers when multiplying. We can move the grouping symbols to make calculation easier, and the product remains the same. So a, and then in brackets, b times c equals, in brackets, a times b times c. Consider the example. 3 times 4 times 5 equals 60, and 3 times 4 times 5 equals 60. The associative property of addition does the same thing. Tells us that numbers may be grouped differently without affecting the sum. A plus, and then brackets, b plus c equals, and then in brackets, a plus b plus c. This property can be especially helpful when dealing with negative integers. Consider this example. 15 plus negative 9 plus 23. And then there's an absolute value there. And 15, and then, that's not absolute value, it's bracket. Oh, you know what? Because of how small the font is, I could be off. I could be wrong because the brackets look like absolute value symbols. That's what happened. I wrote them as absolute value symbols. So they weren't actually absolute value. So their answer is actually correct. Yeah. Not absolute value. You dummy head. Face. Smiley face. Okay. Cool. Are subtraction and division associative? Review these examples. Here's some examples. I don't feel like talking about them. As we can see, okay, I'll talk about them. 8 minus 3 minus 15. Does that equal 8 minus 3 minus 15? Well, you get 20 equals negative 10, so no. And then the division one is also no, so no. As we can see, neither subtraction nor division is associative. All right, distributive property. The distributive property states that the product of a factor times a sum is the sum of the factor times each term in the sum. So a times, and then in parentheses, b plus c equals a times b plus a times c. And then here's This property combines both addition and multiplication and is the only property to do so. Let us consider an example. So 4 times, and then in brackets, 12 plus negative 7 equals, and then 4 times 12 plus 4 times negative 7. And then you get 48 plus negative 28, which equals 20. Note that 4 is outside the grouping symbols, so we distribute the 4 by multiplying it by 12, multiplying it by negative 7, and adding the products. To be more precise when describing this property, we say that multiplication distributes over addition. The reverse is not true, as we can see in this example. 6 plus, and then 3 times 5 in brackets, equals 6 plus 3 times 6 plus 5. So 6 plus 15. Is that the same as 9 times 11? No. A special case of the distributive property occurs when a sum of terms is subtracted. A minus b equals a plus negative b. For example, consider the difference 12 minus 5 plus 3. We can rewrite the difference of the two terms 12 and 5 plus 3 by turning out the subtraction expression into addition of the opposite. So instead of subtracting 5 plus 3, we add the opposite. Now distribute negative 1 and simplify the result. 12 minus 5 plus 3 equals 12 plus negative 1 times 5 plus 3. 12 plus, and then in brackets, negative 1 times 5 plus negative 1 times 3 equals 12 plus negative 8 equals 4. This seems like a lot of trouble for a simple sum, but it illustrates a powerful result that will be useful once we introduce algebraic terms. To subtract a term to sum of terms, change the sign of each term and add the results. With this in mind, we can rewrite the last example. 12 minus 5 plus 3 equals 12 plus negative 5 minus 3, which equals 12 plus negative 8, which equals 4. Identity properties. The identity property of addition states that there is a unique number called the additive identity, 0, that when added to a number results in the original number. A plus 0 equals A. The identity property of multiplication states that there is a unique number called the multiplicative identity, 1, that when multiplied by a number results in the original number. A times 1 equals A. For example, we have negative 6 plus 0 equals negative 6, and 23 times 1 equals 23. There are no exceptions for these properties. They work for every real number, including 0 and 1. Inverse properties. The inverse property of addition states that for every real number, A, there is a unique number called the additive inverse, or opposite, denoted by negative A, that when added to the original number, the results in the additive identity, 0. A plus negative A equals 0. For example, if A equals negative 8, the additive inverse of A is 8, since negative 8 plus 8 equals 0. The inverse property of multiplication holds for all real numbers except 0 because the reciprocal of 0 is not defined. The property states that for every real number A, there is a unique number called the multiplicative inverse, or reciprocal, denoted 1 over A, that, when multiplied by the original number, results in the multiplicative identity 1. A times 1 over A equals 1. For example, if A equals negative 2/3, the reciprocal, denoted 1 over A, is negative 3/2 because A times 1 over A equals negative 2/3 times negative 3/2, which equals 1. And then here's all the properties listed. The following properties hold for real numbers A, B, and C. You have the commutative property of addition and multiplication. You have the associative property of multiplication and addition. You have the distributive property, which distributes multiples into sums. Identity property for addition and multiplication. And then you have the inverse property, where you get the sum, which equals the inverse, or which equals 0, and you get the product, which equals 1. Okay, example 7. Using properties of real numbers. Use the properties of real numbers to rewrite and simplify each expression. State which properties apply. Okay, so this one, to rewrite and simplify, so we have a common multiple, the 3. So if we pull a 3 out, It's the same as adding that. It's negative 8. We can use the associative property. So we can do 5 in its own parentheses. So we take those parentheses, give it to the 5. And that's going to be, there's the plus, and then 8 minus 8. And then that's just going to be 5. Okay, so for this one, I can distribute. This is like saying 6 times negative 1 times 15 plus 9. So I can actually distribute that negative sign to there and there. So then I get 6 plus negative 15 minus 9. Right? And then here I can use the associative property of multiplication and do 2/3 for 7. I'm just combining the fractions because I can do that. And then 7, 4. That's 1. So that simplifies to 2/3. And then this one, I can distribute the 100 to both. So it's 75 minus 238. I don't need to look at that. Evaluating algebraic expressions. So far, the mathematical expressions we have seen have involved real numbers only. In mathematics, we may see expressions such as x plus 5, 4/3 pi r cubed, or the square root of 2m cubed n squared. In the expression x plus 5, 5 is called a constant because it does not vary, and x is called a variable. Actually, it's only constant because we assume constant base. And x is called variable because it does. In naming the variable, ignore the exponents or radicals containing the variable. An algebraic expression is a collection of constants and variables joined together by the algebraic operations of addition, subtraction, multiplication, and division. We have already seen some real number examples of exponential notation, a shorthand method of writing products of the same factor. When variables are used, the constant and variables are treated the same way. So negative 3 to the 5th power is the same as saying negative 3 times negative 3 times negative 3 times negative 3 times negative 3. Which is, and then so x to the 5th, it's right there, and then you get the other one. In each case, the exponent tells us how many factors of the base to use, whether the base consists of constants or variables. Any variable in an algebraic expression may take on or be assigned different values. When that happens, the value of the algebraic expression changes. To evaluate an algebraic expression means to determine the value of the expression for a given value of each variable in the expression. Replace each variable. Hold on. Water. To evaluate an algebraic expression means to determine the value of the expression for a given value of each variable in the expression. Replace each variable in the expression with the given value, then simplify the resulting expression using the order of operations. If the algebraic expression contains more than one variable, Replace each variable with its assigned value and simplify the expression as before. Example 8. Describing algebraic expressions. List the constants and variables for each algebraic expression. Well, anything that's not a number, so the numbers, as I defined before, are 0 through 9. That's a through. Those are constants. And letters, non-numerical symbols, are variables. By convention, the choice. If I wanted to, I could throw down the number 9 and say, oh, this is a variable 9. So I don't need to really do that. So 4/3 pi is constant, 5 is constant, 2 is constant, and then the m's, the x's, the r's, those are all variables. Okay. Example 9, evaluating an algebraic expression at different values. Evaluate the expression 2x minus 7 for each value for x. Okay, I'm going to do it up here. So 2x, where x equals 0, 1, 1/2, and -4. So 2 times 0 minus 7 equals, I didn't mean those parentheses. Well, that's 0 minus 7 equals -7. For 1, 2 times 1 minus 7 equals, that's 2 minus 7 equals -5. 1/2, 2 times 1/2 minus 7 equals, well, it's 1 minus 7 equals -6. And then -4, 2, -4 minus 7 equals, and that's -8 minus 7, -15. Yep. Okay. Okay, example 10. Evaluate each expression for the given values. X plus 5 for x equals -5. Well, that's just the same as saying, so x plus 5, evaluate it at x equals -5. That's going to equal -5 plus 5 equals 0. Okay, and then the next one is t over 2t minus 1. Evaluated at t equals 10. So we have 10 over 2 times 10 minus 1 equals, that's 20, minus 1, 19, so 10 over 19. So 4/3 pi r cubed, 4 over third, pi r cubed, 4r equals 5. That's going to equal, so r equals, it's 5, it's 125. 125 over 3, 4, like that, pi, there. That's going to be 600 divided by 3, 200 pi. All right, let's just see. Did I do the math wrong? Yep, that's not 600. That's 500. So that's, yeah. Okay, anywho, so that's how you do those. If you want to do the last ones, you can do the last ones. Actually, fuck it, I'll just do the last ones. So a plus ab plus b, 4 ab equals 11 -8 equals, so 11 plus 11 negative 8 plus negative 8. So that's negative 88. 11 minus 88 plus negative 8. So minus 8. So negative 96. 11 minus 96. Is that negative 85? Yep. And then the last one, 2n cubed n squared. Evaluated it. N equals 2, 3 equals. So m is 2, so that's going to be 2 cubed, 3 squared. 2 cubed is 8, 3 squared is 9. 8 times 9 is 72. Times 2 is 144. Square rooted, 12. Nice. Formulas. An equation is a mathematical statement indicating that two expressions are equal. The expressions can be numerical or algebraic. The equation is not inherently true or false, but only a proposition. The values that make the equation true, the solutions, are found using the properties of real numbers and other results. For example, the equation 2x plus 1 equals 7 has the solution 3, because when we substitute 3 in for x into the equation, we obtain the true statement 2 times 3 plus 1 equals 7. A formula, give me the formulae, is an equation resulting in or expressing a relationship between constant and variable quantities. Very often, the equation is a means of finding the value of one quantity, often a single variable, in terms of another or other quantities. One of the most common examples is the formula for finding the area, A, of a circle in terms of the radius, r, of the circle, A equals pi r squared. For any value r, the area A can be found by evaluating the expression pi r squared. 11. Example 11. Using a formula. A right circular cylinder with a radius r and a height h has the surface area s in square units. Given by the formula, s equals 2 pi r plus h. See figure 3. Find the surface area of a cylinder with radius 6 inches and height 9 inches. Leave the answer in terms of pi. Okay, so I'm going to go ahead and do this over here. Let's go down. Example 12. Oops, didn't mean to do that. So cylinder. Do. Not a very good cylinder, but the idea is you have a circle. Actually, I'm going to take a cross section. Like that. So that's basically that cross section is now, it's like a circle. And that's radius r. Here's my origin. I'm going to call it Q because I like the letter Q. And then the outer area of that is its circumference. So the circumference, it's like taking this point, breaking it up. So taking like a pair of scissors, not very good drawn scissors, and chopping this up and then making a straight line, which equals C equals 2 times pi times r, or pi times d, where d equals 2r, which is the diameter. And so when you find the area of a circle, oh wait, never mind. So the circumference is like finding the surface area of that outside of this outer edge, this outer surface of that circle. And if you were to count all of those, if you were to sum all of those up, that would be like getting the surface area. So let's see what their equation is. Let's see if I can see the similarity. So S equals 2 pi r. And then in parentheses, oops, here we go, r plus h, r plus h. So what this is actually doing, so I'm going to distribute. So S equals 2 pi r times r plus 2 pi r times h. So what does that mean? Well, pi r, 2 pi r, we said was the circumference of a cylinder, or circle. So that's c times r plus c times h. C plus h. Or I could have just done that replacement right here. C r plus h. Wow, I hate how I just did that. So that's S equals, oops, S equals C r plus h. So it's the circumference of the circle times the radius plus the height. Well, what does that mean? So C times R, circumference times the radius. That's like a surface area. That's an area. I don't know where I'm going with this, actually. I'm going to be honest. I just thought it was kind of fun. Okay. Not going to go any further with that because it's not really important. So I don't think I had anything with it. So then you just plug in the numbers and then you get the answer. So evaluate. So S equals 2 pi r plus h. That's constant. In terms of the like real cylinder. So that's going to be radius is 6. So evaluated at 6 and 9. So 2 pi 6. 6 plus 9. 15 times 6. 90. 180 pi. Yep. Simplifying algebraic expressions. Sometimes we can simplify an algebraic expression to make it easier to evaluate or use in some other way. To do so, we use the properties of real numbers. We can use the same properties of formulas because they contain algebraic expressions. So example 12, simplify algebraic expressions. So basically what I'm going to do, go to here, 3x minus 2y minus x minus 3y minus 7. Well, we can rearrange the x's. So 3x minus x minus 2y minus 3y minus 7. So that's 3 minus 1 x minus minus y, pull it out in front. So I can either distribute, I could pull it out that way, or I could pull it out the other way. It doesn't matter. So the y, I'll pull it out. So minus y, that's going to be 2 plus 3 minus 7. So that's 2x. That's 2x minus 5y minus 7. Let's take it. Plus x. That's a plus 1. That's a 4. Okay. So those are actually pretty straightforward. So distribute. That's going to be 2r minus 15 plus 5r plus 4. Yep. Example 13. A rectangle with length L and width W has a perimeter P given by P equals L plus W plus L plus W. Simplify this expression. P equals L plus W plus L plus W equals 2 L plus W. Cool. And that is it. Cool. Oops. Let's go ahead and stop.